So now that we've done a little bit with definite integrals, we're also going to talk about indefinite integrals. So indefinite integrals, it's really just a shorthand for the antiderivative, right? We now know that the integral is the same as the antiderivative, more or less. So rather than just writing antiderivative big F, little f, it gets a little crazy what f is which. So we just use the integral notation. But now we use the integral notation without the limits. So if I see this, I'll just put it in a function, right? Okay? This is a number because I've got my limits. Well, we'll just put them in. Let's do from pi to 2 pi. Okay? So I know I can do this integral by finding the antiderivative, right? The antiderivative is negative cosine, right? Because the derivative cosine is negative sine. Okay? And then I evaluate from pi to 2 pi. And what do I get? I get minus cosine of 2 pi minus cosine of pi, right? So then this is negative 1, so negative 1 minus 1, and so I have negative 2. So you see, it's a number, and that is a number. This is area, right? When we know this is sine x, and so if I look at what it's doing between pi and 2 pi, it's actually under the graph, so it makes sense that I have a negative value. However, if I write it like this, what I really have, I don't have any limits. This is just a shorthand for antiderivative. So all I do want to do is I want to write down the most general antiderivative, right? So it's cosine minus cosine of x, but plus a constant, right? So whenever I use the indefinite integral, right? So here's indefinite integral. My answer should be a function, and I always have the plus c. You will get doctor point if you don't remember the plus c. Okay? Whereas a definite integral the number. Now, for the WebAssign, I put a lot of definite integrals, not all of them, of course, but I tried because it's easier to input a number than it is to input some long function. So sometimes you will have to put in a function, but I tried to keep it in mind that you don't want to spend your entire time sitting there typing stuff in. Okay? So that's what we're doing now with the indefinite integral. So if whenever you see something with no limits, all you have to do is find the antiderivative and throw that plus c on the end. So I'm going to do a few. But again, these are pretty much going to be ones which are fairly straightforward. They should look like something on the basic integrals, page, or you should be able to do a little bit of work to make it look like one of those. Okay, for example, something like this. This is also a cube root. Okay, so we have cube root of x plus 1 over cube root of x, right? What are we using here? It's an x to the n. So the antiderivative is going to be x to the n plus 1 over n plus 1. It might be easier to simply write them as fractional exponents. X to the 1/3 plus x to the negative 1/3, right? Because now it looks exactly like x to the n, and I just have to do the x to the n. So you can evaluate, so n over this. And of course you can do that in your head. Okay, so what is this? 4/3, right? So I've got, and it's over, so I got 3/4 x to the 4/3 plus, and this is 2/3, right? So 3/2 x to the 2/3, and there's my answer. Okay? So remember n, we have an n, but actually it doesn't have to be an integer. It can be a fraction. It can be, and it can even be pi or whatever, right? It can be an irrational number. So there's that. Let's do one or two more. Well, let's switch. Let's say 2 root x minus 3 secant x. Okay? So square root of x, right? It's x to the 1/2. And so I have the 2, remember, so this I'm just going to write it as x to the 1/2 here. And the other thing I wanted to mention, as you get used to this sort of thing, do always write the dx. I know it's sort of a pain because you feel like it doesn't do anything, but it's an important part of the notation. So when you have an integral, you have a dx. And the really important thing, the reason you really need it in there, is next semester when you take Calc 3, you're going to have multivariables. So there'll be dx, dy, dz, and then they're going to go away, and then this and that. And it's hard to keep track of it unless you have it. So you will need it in Calc 3. In Calc 2, it's tempting just to drop it because it's not doing anything, but you want to get in the habit of putting it there just so that it's already there. It's an ingrained habit. Okay, so what do we do here? Again, this 2 is just sitting there. And then I have x to the n, x to the 1/2. So 1/2 plus 1, so it's going to be x to the 3/2. And let's put this here so we can see it. So 2/3, 2 times 2/3, right? So you probably just write 4/3, but whatever, I'll rewrite it. Okay, now what about this secant x tangent x? You have to know that the derivative of secant is secant tangent. That's it, I'm done. All right, and I could rewrite it, but I am also now just going to be lazy and change the 2 times 2 to 4. All right, so that's an example. Maybe one more. Again, what have I got here? One more. What's this one? Square root of t squared plus 3t plus 2. Be aware, and we will definitely talk about this, although I know that we talked about how integrals are linear. So if I have the integral of f plus g, it's the integral of f plus the integral of g. That works with addition and subtraction. It does not work with multiplication. Okay? So if I have the integral of fg, it is certainly not the integral of f times the integral of g. So you do not want to do this, the integral of the antiderivative of this times the antiderivative of that. It's wrong. In fact, this you have to do with a special technique called integration by parts that we'll get to in Chapter 7. Okay? It's an important technique because you're going to end up using it all the time when we get there. But it is sort of a bit of a pain. So for something like this, you definitely don't want to think about it that way. You want to just multiply this whole thing out. So I'm going to have, what do I have? Right? So t squared times t to the 1/2. I'm just going to write it because otherwise I'll mess it up. Plus 2 times t to the 1/2. right? And then we add exponents. So this is going to be the integral of t to the 5/2 plus 3t to the 3/2 plus 2t to the 1/2. And then each of these I just do with x to the, or t to the n plus 1 over n plus 1, right? So this is just going to be 2/7 t to the 7/2. This is going to be 5/2 times 3, so that's going to end up being 6, right? And then, oh, we did this one, right? This was part of the other one before. So we're going to have 4/3 here. And we end up with plus. So pretty basic, pretty reasonable.